Hello class, hello Professor Mosby. My name is Stephen Hall and this is my final project presentation for Foundations of Online Learning. Today I am going to talk about graphene, the material of the future. Our first topic will discuss the basics about graphene. So what is graphene? Graphene is a base form of carbon atoms arranged in a two-dimensional hexagonal lattice formation similar to chicken wire. Here you see a computer-generated image of a single layer of graphene. In this model, the balls are carbon atoms and the lines represent the atomic bonds between them. First discovery. Now, scientists have speculated on the existence of graphene for several decades until 2004, when two physicists, whose names I will not butcher, became the first to successfully isolate and observe graphene in its simplest form. This work won them the Nobel Prize in Physics in 2010. So, just carbon atoms. If that sounds familiar to you, it should. Due to carbon's atomic structure, it is able to take on multiple molecular forms known as allotropes. Common allotropes of carbon include diamonds, graphite, and fullerene. Diamonds are made of carbon atoms arranged in a three-dimensional tetrahedral structure. This means that each carbon atom is connected to four other carbon atoms with equal distances and angles between the bonds. These equal bonds make diamonds an extremely hard material. Graphite is also made of carbon atoms, but unlike diamonds, the carbon atoms in graphite are laid out in a two-dimensional sheets with each carbon atom attached to three others. This is very similar to graphene's structure, except the sheets of carbon are fractured and layered haphazardly. The bond between the atoms in each individual sheet are much stronger than the bonds between the layers, making it easy to cleave the layers from each other. Graphite has even been described as slippery. It is most commonly used in pencil lead. Now, fullerene's molecular structure is even more similar to graphene than graphite is. It is comprised of carbon atoms laid out in the same two-dimensional structure, yet the two-dimensional layers are made into three-dimensional shapes. The two most common forms of fullerene are carbon nanotubes and Buckminster fullerenes. Carbon nanotubes are single layers of carbon atoms that are rolled into a cylinder. These can be concentrically layered, creating a very strong material. Buckminster fullerenes are a single layer of carbon atoms that are arranged into the shape of a 32-sided polyhedron. It is comprised of 12 pentagon-shaped faces and 20 hexagon-shaped faces, and actually resembles the shape of a soccer ball. It is named after American architect Richard Buckminster Fuller because it resembles the shape of his famous geodesic dome. They are also commonly referred to as buckyballs. Notice that the bonds are not identical in either form of fullerene. So with all these common forms of carbon, let's talk about what makes graphene so special. So what is special about graphene? Like with diamonds on a three-dimensional plane, the carbon atoms in graphene have bonds of equal distance and angle on a two-dimensional plane. Compare this with fullerene, where the bonds are not identical, or in graphite, where the bonds are incomplete due to fracturing and unorganized layering. These equal bonds afford graphene some unique properties, such as strength, electrical conductivity, the ability to conduct heat, and transparency. Because the bonds between graphene carbon atoms are equal, it is an incredibly strong material. So how strong is graphene? Well, in 2008, several scientists at Columbia University tested the strength of graphene and found it to be the strongest material ever observed. Professor James Hone called graphene 200 times stronger than steel. To put that into perspective, Professor Hone used this visual, stating that it would take an elephant balanced on a pencil to break through a sheet of graphene the thickness of saran wrap. So this is an extremely strong material. Graphene also has great electrical conductivity properties. Its atomic structure provides virtually zero impedance to electron flow. This allows it to conduct electricity better than any known material and 100 times faster than silicon, the material most commonly used in integrated circuits and computer chips. It also conducts electricity without overheating, which is one of the biggest concerns for current miniaturization of modern electronics, so this could potentially solve this issue. Graphene also conducts heat better than any known material. Now, not only is graphene the strongest material and the best conductor of heat electricity, but it is also more transparent than glass. So let's discuss the real-world applications for graphene. Graphene has a lot of fascinating properties. It's transparent, strong, and conducts heat and electricity extremely well. How will we be able to use it? Well, graphene will be used in energy storage, computer circuits, corrosion protection, flexible displays, and aerogel, just to name a few. Energy storage. We are beginning to reach a limit to the capabilities of lithium-ion batteries. However, Korean scientists have developed an all-graphene battery that can store as much energy as a lithium-ion battery, but it can be recharged 5 times as fast. This will prove useful in electric vehicles, personal electronics, and any other device where charging time is a concern. Computer circuits. Current silicon processors maxed out at around 4 GHz speed almost 10 years ago. Processors have only been getting faster by using multiple cores that operate in parallel. IBM has created a graphene computer chip capable of 155 GHz. This, combined with the lack of overheating, will revolutionize the capability to make smaller and faster computer chips. Corrosion protection. Because carbon is not a metal, it does not corrode in seawater. Australian scientists coated steel with a layer of graphene, making it corrosion resistant. This is extremely significant because the #1 most expensive cost to ship maintenance is corrosion repair. Flexible displays. Graphene's material strength, transparency, and conductivity are allowing scientists to create extremely thin, flexible display screens and touchscreens. This could lead to screens that you could roll up and place in your pocket or a bag, and more importantly, it could lead to a smartphone with a screen that doesn't shatter when you drop it, which is of course everyone's dream scenario. Graphene aerogels are created by freeze-drying a gel solution of graphene. The resulting material can support 2,600 times its own weight and can absorb 112 times its weight in oil, making it a possible solution for any oil spills in the future. It is also the lightest solid material in the world. In the picture, you can see a 1-inch wide cube of aerogel resting on the fiber strands of a blade of wheatgrass. So with all the amazing things that graphene can do, I am sure you are wondering why it's not being used for everything already. The problem is that graphene is still extremely expensive to make and is difficult to make in large quantities. Scientists are looking to develop methods for producing graphene on a large scale. Some of the current methods are chemical vapor deposition, microwaving graphene oxide, and contained detonation. Chemical vapor deposition is currently the most widely used method for producing graphene. It is accomplished by dissolving carbon-filled gas into the surface of a superheated metal. When the metal cools, the carbon is forced out and coats the surface of the metal as a graphene layer. This layer of graphene is extracted by chemically etching it from the metal surface. Another more recent method to produce graphene is by microwaving graphene oxide. Graphene oxide is created when chemicals are used to exfoliate sheets from graphite. This is a fairly affordable process and the easiest way to make big sheets of graphene. The problem is that graphene oxide is a degraded form compared to pure graphene. Engineers at Rutgers University were able to remove nearly all oxygen from graphene oxide through this microwave process, leaving exceptionally high quality sheets of graphene. The most promising new method of producing graphene is through contained detonation. Physicists at Kansas State University were able to produce graphene by detonating a mixture of oxygen and hydrocarbon gases in a container. This method is promising because the graphene produced is pure and is believed that it can be expanded to an industrial scale. So as graphene is the material of the future, who is going to make it? Currently, the main participants in the graphene production industry are chemical engineers and physicists. I intend to become a chemical engineer after I obtain my degree and complete my Navy career, working to develop better ways to produce graphene. I will now discuss several statistics regarding the chemical engineering field, including salary, employment opportunities, and career paths. The most current salary information I could find about chemical engineers was from 2015. The median salary for chemical engineers was $127,000. For someone with no more than 3 years of work experience, the median salary was $71,000, and for someone with 16 to 20 years of work experience, the median salary was over $133,000. So this field gives a lot of room for growth. Chemical engineers working in research and development, which would be the people working in graphene production, had a median salary of over $122,000. Looking at employment opportunities, the unemployment rate for chemical engineers was only 2.8%, significantly lower than the national average of around 5.3%, so the job market is good for this field. Looking at possible career paths, chemical engineers most commonly end up in jobs in consulting, corporate or general management, plant management, project management, engineering process management, and of course research and development, which is the field I hope to enter. Well class, this concludes my presentation on my career interest in graphene production. Hopefully you are as excited as I am about the possibilities that graphene has for our society. Thank you very much for your time.